Hello. So yes, I've already been introduced, I guess. My name is Heather Miller. I'm a PhD student at EPFL, which means I don't do any sort of commercial anything at all. I teach people a lot of things all the time. I do research, and I've contributed a few things back to Scala over the course of the time that I've been at EPFL, some things that people might be familiar with. I was one of the people that worked on the Futures framework, or the Futures library in Scala Concurrent. I worked a lot on the serialization framework and serializing these function things that you're going to see here. And I wrote a lot of the documentation that you probably had to painfully read through. So if anything was unclear, it's maybe my fault, and I blame myself. You can tell me if something needs to be improved. I'm happy to hear about it. And we also take contributions, so if you ever find some documentation thing or anything else that you think could be improved, either let me know, make a pull request. We have lots of repositories of documentation all over the place. So real quick before I start talking about this functional stuff in distributed programming land, I wanted to have this quick, shameless kind of plug. I'm organizing a conference that's it's totally a nonprofit, academically oriented event. It's called Kurion. It's a conference that cares about the intersection between programming languages and interesting problems in the real world. And I wanted to show you, we have some really cool speakers that are really important and influential. And I think that anybody who knows about, oh no, what's happening? Anybody who knows about functional, oh, this is not working. Something is going on. Okay, I'm not going to show you this because for some reason I can't use my browser. So we have people like Phil Wadler, who made monads known in programming land. We have people, and he contributed a lot to the ideas in Haskell. There is Brendan Eich, who famously created JavaScript in like a weekend. We have Bjarne Sustrup, who invented C++. A lot of very important people in programming languages are going to be there, and there's also a lot of people presenting commercial work that makes interesting use of new ideas, usually from academia or people who have brought ideas to academia. So it's kind of like an academia meets industry sort of conference, and I encourage you to look it up or attend. It's being held in Prague. So it's not super far away, but it's not exactly close either. Anyway, so let's talk about what I'm here to talk about in the first place. So this talk is about doing functional programming in a distributed way. I'm sorry, doing distributed programming in a functional way, excuse me. And to start, this is about research. I'm a PhD student. I don't do anything in any commercial sense. So this is just like a fun talk about a project that I've been working on, some ideas. This isn't necessarily anything that maybe is even a good idea. It's research. So there's also a paper about this in case I don't give you enough detail here and you have deep questions and you either can ask me more about them or look them up in this paper. But first, to talk a little bit about what where this comes from. So in my PhD, I've been working on a serialization framework that some people may have heard of. It's called pickling, and the idea behind this framework was mostly to provide a serialization framework that would help people who have to build distributed systems. And what do people who build distributed systems care about? Typically, it's like how fast things are happening and reducing the amount of stuff that's sent over the wire, because what takes the most time in a distributed system is usually sending things over the wire and the latency that comes from that. So let's very quickly serialize things into very small, whatever like blobs of data, whatever you want your representation to be, and this framework that I worked on, it does most of this at compile time, so it's performant. It does all kinds of inlining and things, so you're not doing stuff at runtime to figure out what you're trying to serialize. And then also, it's very extensible. It's based on type classes, so you can override the default functionality of this framework very easily. You can also provide different formats to serialize to anything that you want. It doesn't have to be binary. It can be your own invented format. It could be JSON. It can be whatever you want. So it's extensible in a few ways, and that's what makes this thing interesting. So that's one thing that I worked on. Another thing is it's got a funny name. It's called spores. The idea behind this was to make it reasonable to serialize closures. I'll talk a little bit about why that's actually not simple. But there's these two projects, right? So the first one is serialization, or pickling, and the second one is called spores. And in this talk, basically, the next step of the work that I've been doing is bringing these two things together into a programming model. So this talk is about this programming model that builds on this basis of serializable functions to provide a substrate that one can maybe more easily build functional distributed systems on top of. And these ideas, sort of the things that these ideas that this sort of design gives you more easily is fault tolerance. So you know, if one machine somewhere crashes, being able to recover from that, right? And then speeding things up by doing things in memory more, and then also by pushing more types through the stack, debugging becomes a little bit easier, especially when you have stack traces from different machines and stuff. You know, you run into fewer runtime errors, hopefully, is the idea. And one important point is that this is done in a clean way that's as stateless as possible, right? And I have to thank Databricks. I worked at Databricks for a little while, and I did this project mostly while I was there, just being a research intern, so this didn't go into anything production there either, but they funded it, basically. So the fundamental idea is that we invert the actor model. So everybody knows how actors work, I hope, right? Generally that you do. So it's more like a dual to actors, and I think it's a nice compliment. I can talk about why later, but maybe I can tell you perhaps how this is true. So if we know from actors that you have this thing called an actor. Usually it encapsulates some kind of state. You're using it to do some concurrent thing, and the actor kind of does stuff in a way where you think about it sequentially, but to that state, right? They encapsulate state and behavior, and they're stationary. They stay on one machine. You're sending messages back and forth over the wire, right? So they exchange data like asynchronously via messaging. Whoops. Oh no. How does this? And this function passing idea is basically the inverse of all of that. So rather than encapsulating some kind of state, it itself is stateless. And it's built on this idea of persistent data structures. So everything that you do is a transformation upon some immutable piece of data in this world. So you keep the data where it is, and you do transformations on this data, and you use functions to make these transformations. And instead of passing data around, you're passing functions around that represent sort of these transformations. They're exchanged through asynchronous messaging. And this is not a new concurrency model. I want you to understand that first. I'm not presenting a new idea of concurrency. This is just a model for programming with data, not a new model of concurrent processes. I can go into some motivation about why it's designed this way. I don't want to run out of time though, so I'm just going to say a very quickly. There's this note on distributed computing that was written in 1994, and we keep on making the same mistakes that they warn us about in 1994, like in 2015. So really what they're arguing in this paper is that there's a model of local and remote, and that basically there are these things that happen, latency, memory access, partial failure, and concurrency, and because we are trying to merge local things with remote things, we like to pretend that something that we're dealing with locally isn't really remote. I'm sorry, something that we're dealing with remotely isn't really local. What am I saying? Remote and local objects. So I have something that I'm playing with on, it seems like it's on this machine, but it's really secretly somewhere else. And all of this network communication has to happen in between, but it appears to be a local object, but really it's a remote one. And all of this stuff that happens, latency, failure, these things are all hidden. You have no idea that you're dealing with something remote. And this paper argues basically that that's a bad decision. That's a bad design decision if you hide this completely from the programmer. They say that a better approach is to accept that there are irreconcilable differences between local and distributed computing, and that you have to be conscious of these differences at all stages of the design and the implementation of a distributed application. So not a system, like not you're building the next Spark or Hadoop, but like you're just building something on top of it, right? So the people who are writing these programs should be aware that latency or communication or network communication is happening. So rather than trying to merge local and remote objects, engineers should be constantly reminded of the differences between the two and know when it's appropriate to use a remote object or a local one. So they make, and basically a lot of the arguments that stem from this, they make a lot of arguments about sort of why things don't work or why they're not performant or why they failed in the past, right? And they argue that this is the reason. So in our model, we try to keep track of all of these things and make sure that there's a clear distinction between when something is local and remote. We try to make communication explicit, and I'll show you how. So what does it look like? So this model has two ideas, right? Like I said, it starts with this idea of data being immutable and stationary, and that you have these functions that are portable, that you can send them over the network. And basically what you're doing is you're applying them to this stationary data that's distributed all over the place, right? Right now, we're calling this data, like this stationary immutable data silos, and we're calling the functions, whoops, and we're calling the functions that we're sending around spores. So when I say silos, I mean the data. When I say spores, I mean the functions that we're applying to the data. So we'll start by explaining each individual piece. So to start, like I said, there's this thing called a silo, and this is what the model kind of looks like. If you're familiar with Akka, there exists this idea of a reference, like an actor reference, right? So in our model, we also have something called a silo reference. This is a handle to your data that may be somewhere else. And the data itself exists in this thing called a silo. You don't have any access to it except through this thing called a silo ref. And the idea is that you build basically a DAG, a directed acyclic graph of transformations on this data. And each time you apply just like you have a list and you apply, you pass a function to a higher order function like map, and you get back a new list. This is the same idea. Every time you apply a function to a piece of to a piece of distributed data through a silo ref, you get back a new silo. It's just, and there's just this relationship which represents the function transformation, and you build these graphs, if that's clear, of basically computation graphs. And also in this picture, for the sake of like visualizing things, I'm only going to ever visualize things with like 2 nodes, but this can extend to an arbitrary number of machines. So there are 3 important primitives. So beyond there being this thing called a silo and this thing called a spore, there are 3 important primitives that you have to know about to kind of get an idea of how you can build programs in this model. One is called apply. Oh, sorry. We know that the silo ref is a reference to this piece of remote data. So there's this function called apply. For the sake of the examples I'm going to show you, assume that it takes two functions, 2 spores, and it returns you a new silo ref. Okay, just for now. And what's important about this is that it is a lazy sort of combinator thing. Basically, what it does, it makes it possible to build. Does anybody know Spark? Are you familiar with it? I mean, everybody hears about it all the time because it's like a hot thing. But if you know how it works, this whole model is very much like a generalization of Spark's programming model, but boiled down into something much smaller, like at the size of a middleware or something. So in Spark, you might know that if you have an RDD, a big distributed array, so RDDs are like a distributed list, like you have a big data structure that you distribute over many machines, and then you can apply a map, do like a distributed map on it, and what you get back, it immediately returns, and nothing happens. Computation only happens when you force it via some other sort of computation like a reduce, okay? So Spark is lazy. In the same way that Spark is lazy, this model is also lazy. So whenever you want to transform the data, whenever you want to basically do this thing where we add new nodes to the graph, this is all happening lazily. So really on one side of forget about the illustration, we're basically just building this until we kick off the computation remotely, right? So the apply function does that. So you use this function to implement, if you're going to implement something like Spark, you use it to implement something like this distributed map function. And the idea is that these two functions that you pass to it, one is basically like the framework logic, and the other is the logic that the user would pass. So if you're going to implement a distributed map, you would want a user to be able to provide a function to that map function, right? That high order function map. So it takes these 2 things, and it basically builds a new node in this computation graph. The next thing is called send, and that's what actually kicks off computation. This is eager. This sends the function, basically all of the functions that have been sort of built up and queued up. It sends it over the network. It returns a future that should have the type of the value that you want back. So if you have a big distributed collection and you're using this framework to implement it, you can think of it as being like this the send thing, being like the result of calling reduce or something on it. So I just want to find the sum of a very large distributed collection in memory. I just get back one integer or something like this. So you use this to get your results back. And it's done asynchronously with futures. And the last one is actually very important. If you actually have ever had to use something like Hadoop or Spark, then you might know that something like joins happen, shuffling happens. You have to send data around the network. I'm not going to get too much into this because when I have to teach people about Spark, they get headaches when they have to figure out when shuffling happens. But this primitive makes it possible to implement things like joins, so that you can do this sort of shuffling. So we call it flat map, and it takes a spore which has a very important type. The type of the spore, it would operate on something called like this T, and it returns a scalar-ref. That scalar-ref does not have to be on the same machine. That makes it possible to shuffle data over the network. And the way that this thing is implemented, it will basically, like in a streaming fashion, serialize data to the node that it should be on, right? Yeah, I just explained that. So here is another picture of this thing working, how it works. So now I have types, and this is actually kind of important because this prevents all kinds of issues when, like all kinds of runtime issues from ever occurring, because you can never apply a function to data that like has the wrong type. It just doesn't compile, right? So you're never left with just sort of the network hanging because you received a message of the wrong type. It just statically doesn't ever allow this to happen, right? So here, let's just say we have a scalar-ref of some type T, which obviously points to a silo that we've somehow filled up somewhere called also of type T. So let's just say that we're going to do sort of a map function, and like we're forcing it. So assume that this is, for now, this is eager, just to show you what's going on. The way that it works, the way that it unfolds over time, if you somehow force this, is you send this function that has type from T to S, right? So this is a scalar-ref of T. You're transforming your data from T to S. So you get back a scalar-ref of S. And you can do whatever you want with that. You can keep on building up the stack, adding more nodes to it, whatever. But let's just say somehow now I force this computation to kick off. Eventually, this thing gets filled up, and this reference completes and points to this thing successfully. So even before this thing is ready, even before this silo-ref this silo is computed, this silo-ref here is available. You can use it. You can do all kinds of things with it, and the framework basically knows how to queue up any messages that need to be sent to this guy until that guy is available. And these things can also, like I said, exist many on one machine. This is a very simplified picture that I showed you earlier. And this is actually, this model supports something very peer-to-peer. So you can have many silo-refs on different machines, and you can have many silos on different machines, and silo-refs pointing to each other, like to other machines. So it's not necessarily like only Spark or something like this, where if you know Spark's model, it's like a master-worker kind of model, where you have a driver program that's distributing all kinds of work to a bunch of worker programs that have the same, that do the same thing. So it's like master slave, master worker. This framework also allows you to do sort of peer-to-peer kind of stuff where you don't have like some formal master existing. Okay, and these spore things. So I told you that they're functions that you can serialize, and why is that important? So it's actually, so first let me show you what they look like, and then I'll explain why they should exist. They're actually, the idea is that they try to control the environment that a closure can accidentally capture. This is problematic in Java serialization land, where you can pull in your entire program in the form of like the object graph of everything and accidentally be sending that over the wire all over the place all the time. So this prevents that from happening, or it tries to, by failing to compile if the environment is not explicitly specified. So I can't accidentally capture all of Wikipedia by just going like wikipedia.length and referencing that inside of my closure, right? This creates an object graph that pulls in everything. In this case, what it does is it has two parts. It has this local value definition like called the header. So you have a list of values that represent the environment that you want your closure to reference, okay? And basically, we statically check to make sure that everything in here only references this stuff, otherwise it doesn't compile. And that saves so many headaches that it's actually unbelievable, especially if you use Spark. And the only thing that you need to have is this spore header. So the idea is that you have this thing called a spore, you have the spore header, and then you have the spore, the closure itself. So the second piece is the closure. So you have the header, the closure, and it all lives in this thing called a spore, or whatever, and the spore, it's got the spore marker on it. And so important guarantees that this thing provides, or that these spore things provide over closures, is that it makes sure that everything that you capture in the spore header that the initializers for those things are called when the thing is created. So that also means that your object graph can't change over time because it prevents things like vars from existing. So you can't change like the shape of your object, right? It also makes sure that the references to these captured variables don't change, because it's not, like I said, no vars are allowed, like no lazy vals. All of these things aren't allowed. Only an environment that is effectively immutable is allowed. And actually, the evaluation semantics are also important, because this is only static checking. It does no transformation of any kind. That means that if I just go back to this example, I remove this spore thing here. This behaves the same as just a normal block. If you know what that is in Scala, you do like, val s equals, forget about this, and say like curly brackets in this thing here. It behaves exactly the same as that. Like I don't do any transformations statically so that this becomes something else. This has the same evaluation semantics as a normal block in Scala. And spores and closures are created in that if you don't want to have to deal with writing this spore keyword all the time, there are implicit conversions. So long as something like Spark has like a map method that requires a closure, the static checking still kicks in, because an implicit conversion happens, so that users don't have to maybe write this spore thing if they don't want to. So benefits of these spores is that the environment, everything that you capture with your closure, it's always declared explicitly. So A, you know what it is, and B, it prevents like crazy object graphs from accidentally getting pulled in. And we can also statically ensure with this framework that everything that's captured is serializable as well. So you can't like have a runtime error for capturing something that you don't that doesn't extend serializable, because actually we use the pickling framework to do all of this. There's a paper if you care to read more about it, and also a SIP somewhere. Maybe I can show then, now I showed you what these silo things are, I showed you what spores are, and you guys kind of know what Spark is, right? Or this idea of distributed collections, like the idea of having a big list that you distribute the data evenly over many machines, and then you somehow deal with doing the computation over all the different machines and merging the results together in a distributed way, right? So if you know these three things, I can make a cute little example to kind of show how you might want to do like a map, and like a reduce, for example, on a distributed collection, or an example distributed list, and how you would use this model and what it would look like. So imagine that we're trying to implement something like a map and a reduce. Remember that these things have to be spores, because that's what the framework requires. And the way that this would look, so assuming that you start with a silo ref that points to a piece of data somewhere, but it's of type list of int, right? It could point to many pieces of data, many distributed, many lists distributed over many machines. And you call this apply function, and what happens is that basically a new node gets created, like a new silo ref gets created as a result, and the new silo ref contains the functions that needed to be used to create it. So if I wanted to do a map, like I said, like a map on an RDD or something like this, and I pass a function f to it, this little node, the silo ref thing of list of int, the resulting one, would contain those things. So I know exactly what logic to basically transmit over the network and apply to my distributed data. It's these two things, I have to compose them together. Same is true if I do another map. I have a reference to the map logic, right? This map function, like I said, just imagine it's implemented already for you, and that it's implemented in the form of a spore, and that you have this other user-defined function that you would then pass to map, right? Now, they're all the same. They just kind of build a new node in this DAG. This also can be not a line. This can be, like I said, a persistent data structure that's like tree-shaped. But for the sake of this example, we're just doing a map, and a reduce. So when we get to the reduce, something different happens. We end up with this node, right? A new node that represents, that holds on to this reduce logic and holds on to the function that's passed to it. But now, this thing would be implemented via ascend, right? So these are implemented with applies. This is implemented with ascend, which means that it's eager, right? So this is the thing that kicks off all of the computation. It goes back through the DAG that we've created, applies all the functions together, and then it sends it over it sends it over the wire, basically. So if there existed this piece of data somewhere else that this scalar-ref points to of the same type, when you call this send thing, it kind of collapses this DAG, sends over sort of the many functions applied together. It sends it over to the machine that holds, or all of the different machines, perhaps, that hold. So like I said, this can be many pieces of data. It doesn't just have to be one. But it would send it to the machine that holds the root piece of data, this first silo, which contains this list of integers. And it sort of causes intermediate ones to be materialized. So all of these things get eventually created, and then these references also eventually complete. So I could also, like I said, I could take this guy, if I have a name for it, and start applying more map nodes or reduce node or whatever. I can make I can branch off of that and make a new one, a new graph. And when this is done, when the result is completed, when all of these things have been materialized, the result is returned back to this original scalar-ref guy who completes it with a future, if that's clear. And so this is I said earlier that this somehow helps with something called fault tolerance, and that's because what we're doing is we're not actually doing any computation most of the time. We're keeping track of the computation that should take place eventually. So this is how Spark actually works. These things are basically all of this data structure that we're building. It's all serializable because it's all built with these spore things, right? And it's all just a persistent data structure that represents sort of transformations on big pieces of data on the other sides of the network. And oops, we have to. 1 sec. Oh, sorry. And this helps with fault tolerance because what these things are, what those little DAGs are, they're actually lineages. So lineages in Spark are what make it possible to keep on recomputing individual pieces of data. So scalar-refs and silos relate to each other because, like I said, they're this distributed data structure, and it's everything that you do on this thing is basically making a new node in this graph, which is actually a lineage. And this is how, well, this actually comes from the world of databases, but this is how you can keep on recomputing a piece of data in case a node fails. So if something fails, if we know that something has crashed somewhere, we have all of the information about how to go about recomputing that piece of data. So just traversing this simple data structure that represents silos, or the scalar-ref data structure, this is actually a lineage. And since the lineage is composed of these spore things, you can either serialize it, send it to another, you can serialize the entire lineage, send it to another machine, and restart computation on that other machine somehow if you know how. Or you can just persist it to disk, and if something crashes, you can just read again from that disk, right? So this is why fault tolerance exists, and it's made a little bit easier. So yeah, I'm summing up. So in summary, this idea of this model has these things called silos, which are immutable, persistent data structures, and they're distributed. They reference distributed data, and they themselves are just transformations upon that distributed data. And everything, all the operations that you would be doing to this distributed data, is implemented in the form of these spore things, so it's serializable, which means you can send it around to save it, to keep track of it. And taken together, the idea here is that we can basically provide something that like a base programming model to build systems like Spark on top of that can make things like fault tolerance easier and also speed up things like serialization. So yeah, there's this paper again, if you're interested, but that's it. So if anybody has any questions or think that it's a bad idea, just tell me, or you can also tell us on this mailing group. Yep.
So I have two questions about infrastructure, how you kick off, let's say, machines with instances of Spore, let's say. Okay. And the second, how you encrypt data over the wire. Is there any function like this?
What do you mean, to serialize things?
Yeah, when you send the data between machines.
How do I do that? I use Netty. Okay. Okay. That's the one dependency that I have. That's not Scala. Okay. I mean, I have just Scala centered library and Netty, and that's how I do this sort of network communication. And then, what was the first question?
What do you need on the machine to use it as a node?
What do you need on the machine? Do you mean like how do I start something as a node?
Yeah.
So actually, starting these things up is basically you know I mean, right now it's because this is an experiment. It's not like a push button solution. You just push and it makes a cluster for you. You have to start some machine somewhere, have an IP address and a port, and you basically have the same class files on that machine as well. And so you know how to send messages back and forth between it. That's clear.
Okay, thanks.
Yep. I think we have time for like maybe one more question if it exists. Otherwise, how do I print stack traces? I don't do anything to do that right now because I just want to make sure that this thing even works, period. So in terms of debugging, that's a wonderful question. I could do lots of things, but I haven't done anything yet to make it easier to see the stack traces. This is not like anything I suggest anybody try to use right now, ever, at all. I just want to see if this idea makes sense. Yep. No. And I can tell you why. Mostly it's just binary compatibility. They have like questions on their mailing lists like every few hours or something about somebody accidentally capturing stuff and things are slow and I don't know why. They would have loved to use this thing if it existed 6 months or a year earlier, but it didn't. And now they have this binary compatibility problem where they have all of these guarantees and they can't really readily upgrade until like the next major version if they want to. So it's up to them if they want to do it, but not now. And I think I'm out of time, so thank you.